This is Jambo Radio.
Hello, and welcome to the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. Of course, on this show, what do? Well, we explore the development of science and technology, and especially the implications these have for everyday life. And today, since everybody seems to be once again excited about space, our topic will be probing the planets. Yes, we will be discussing about new and innovative ways to do that. And we'll learn from today's guest, who we will introduce in a moment, a lot more about that. Of course, something that often comes up when talking about space and about the cosmos is this terminology. Maybe you've heard it before. It's the light year. Light year. What on earth does that even mean? And that's our question for this week. What on earth is a light year? You could say that's a little bit of a trick question, and it has two different sides to it, as you'll learn in today's show. There's a serious answer, and there's a not so serious answer to that question. So stay tuned to know what these answers are. Well, of course, I'm your host, Dr. Adetunmise Dada. I'm a lecturer in optics at the University of Glasgow, and I'm your host for today's show. And this is the Science Show on Jambo Radio Scotland. So first, let's do a quick run through of what we're going to be enjoying on today's show. As usual, we're going to start with the science news highlights, after which we're going to have an introduction, or if you like, a meet and greet with our guest on today's show. And then we'll go into a discussion on astrophotonics, where astronomy meets modern optics. And this will be, of course, a part of our interview with our guest today. And after that, we're going to have another part of the interview, which we will explore our guest's research. He will be explaining to us what he does and how he does it. And then in the end, we're going to enjoy, as usual, a few science jokes. After that, we're going to also have a freestyle. We're going to vibe to a beat. We're going to sing a song to a beat about science, about especially the topic that we'll be covering today. So you won't want to miss that as well. Great, fantastic. Let's start then by having a quick introduction of our guest on today's show. Well, our guest for today is very special indeed. His name is Professor Robert Thompson, and he's a professor at the School of Engineering and Physical Sciences at the Herefordshire University in Edinburgh. He leads the Phi group at Herefordshire University, and he will be telling us what Phi actually stands for in a moment. So you're welcome, Professor Robert Thompson. How are you today?
I'm doing very well, Dr. Dada Adetunmise. Thank you very much for the invitation to come here and speak to you today.
Great, it's lovely to have you here. So what does Phi stands for then? The name of your group is Phi. So what's that? What's Phi?
Yeah, so Phi is short for photonic instrumentation. So the group that I lead at Herefordshire is interested in developing instruments for a whole variety of different applications, including the astronomical applications that you talked about, but developing instruments that really allow us to harness the power of photonic technologies to enable better measurements of different things effectively.
Fantastic. Yes, we'll be learning a lot more about that in the course of today's show. That's great. Now, the question of the week again, as I said earlier, what on earth is a light year? Perhaps we'll maybe explore that a little bit now. So, what's a light year? A year, of course, we all know is a measure of time, isn't it? But a light year, although it sounds like a measure of time, it's actually not a measure of time. So this is like the serious answer. A light year is actually a measure of distance. It's the distance that light travels in 1 year. Now, light is the fastest traveling, the fastest thing you can think of. Actually, literally, nothing travels faster than the speed of light. And the light, speed at which light travels is 299,792 kilometers per second, not per hour, but per second. That is insanely fast. Now think about it. The sun is 93 million miles away. So how long do you think it takes sunlight to travel from the sun to us on Earth? Well, it takes about, at the speed of light, it takes 8 1/3 minutes. So 499 seconds to get to us. So think about it. To put this in perspective, if you drive at about 93 miles an hour, which is illegal in most places, but assuming you could, at 93 miles an hour, it would take you 1 million hours to get to the sun. Now, how many years is that? Can you guess? Well, that's about 114 years. Can you imagine? Imagine trying to get to a place traveling for 114 years. So that's just gives us an idea how fast light travels. Now, planes fly at about 460 to 575 miles per hour. And let's say, okay, let's round it to 600 miles per hour. That's really fast, isn't it? Now, to take a plane about 155,000 hours to get to the sun. That's about 18 years. So just to give you another example of just how fast light travels. And yeah, it takes light 8 minutes to take, to do that trip. So yeah, that's it. That's the serious answer to the question. But later in the show, we're going to be sharing the not so serious answer to that question. So stay tuned for that. So for now, let's get into our science news highlights. So today on our news highlights, we have 3 headlines. The first one is a bit of a sad news. It is NASA calls off moon rocket launch. Aww. The second one, plasmas could be used to make the world's most powerful laser. And the third, the James Webb Telescope spotted CO2, that's carbon dioxide, in an exoplanet's atmosphere. Now we're going to learn more about that in a moment. So the first one, NASA calls off moon rocket launch. You remember last week that we announced that there was going to be a launch on Monday of a rocket to do a sort of an excursion around the moon. Well, unfortunately, this has had to be called off. Well, because the controller struggled to get one of the rocket engines to cool to its correct operating temperature. So NASA has called off that launch, and this is just for the sake of safety. This is a bit of a shame because this maiden flight was part of NASA's Artemis program, and it's meant to be just a demonstration with no one on board. But of course, ever more complex missions are planned for the future that will see people actually live on the lunar surface for weeks at a time. So exciting times are still ahead. We just have to wait a little bit longer. So the second item, plasmas could be used to make the world's most powerful laser. Well, if you've been following this show, you'd have learned a thing or two about lasers. But it's interesting because here the story says that because plasma can shape very intense light without being damaged, it could be used to make components for lasers thousands of times more powerful than the strongest ones that exist. Now, why is this the case? Well, Matthew Edwards and Pierre Mitchell at Lawrence Livermore National Laboratory in California proposed a laser design that includes components made from plasma, a state of matter similar to a hot soup of charged particles. They calculated that because plasma can reflect and focus very intense light without itself being damaged by it, this method could help build lasers thousands of times more powerful than the strongest ones. Now just think about this for a moment. What's the strongest laser that exists now? Just to give you an idea, I saw a headline somewhere which says that there's a petawatt laser. So up to 10 petawatts, probably more. Just think about that. That's enough to vaporize matter. That is insanely powerful as well. So to give us, to put that in perspective, so the Earth receives only 1/billionth. In fact, if you divide the amount of the light coming out from the sun into 2 billion parts, the Earth gets only one tiny slice, just one of that. So 1 out of 2 billions. Now, of course, the rest of the energy goes off into space, but the tiny, fraction that gets to the Earth, can you guess how many watts that corresponds to? Well, 1.7 times 10 to the 17 watts. So that's something like 100 times of the the petawatt, that we mentioned earlier. So just imagine if you get lasers that are then much brighter than that, it means these lasers will be so powerful. They could be powerful enough to illuminate a planet such as the Earth. That's just mind-boggling, isn't it? That such devices can be developed with science and technology. Anyway, the next headline says, the James Webb Telescope spotted CO2 in an exoplanet's atmosphere. So that's interesting because usually CO2 is a gas that's often, associated with the activities of living organisms. So they say it's the first definitive detection of the greenhouse gas as a planet outside the solar system. The James Webb Telescope found signs of carbon dioxide in the atmosphere of the gas giant exoplanet called WASP-39b, WASP-39b. Now this telescope has gotten the first sniff of carbon dioxide in the atmosphere of that planet, and the scientists behind it say, well, it's incontrovertible. It's there. It's definitely there. That's the words of the co-author, Peter Gao of the Carnegie Institution for Science in Washington, D.C. And he also said there have been hints of carbon dioxide in previous observations, but never confirmed to such an extent. So this is really big news. This is exciting. Now, just a little bit more on the James Webb Telescope, or JWST. This was a telescope launched in December 2021, and it released its first images in July 2022, so quite recently. So for about 8 hours in July, the telescope observed starlight that filtered through the planet's thick atmosphere as the planet crossed between its star and the telescope. And as it did, molecules of carbon dioxide in the atmosphere absorbed specific wavelengths of that starlight, and that's how they are able to tell for sure that carbon dioxide exists on the planet. So that's something very interesting as well. So, fun fact about exoplanets. Perhaps Professor could offer to tell us, what is an exoplanet? Because I know this is one of the things that you are actively researching yourself. So, an exoplanet.
So an exoplanet is an extrasolar planet. So that's a planet that exists outside our own solar system. So it's not orbiting our star, the sun.
Yes, thank you very much. That's interesting, isn't it? I mean, of course, there are so many of them out there. The closest one to us on Earth is Proxima Centauri b, and that's located just 4 light years away from Earth. So that's the time of the light years, because the distance is so great. You need a unit that makes sense, and it takes light 4 years to get to the next planet. That's interesting, isn't it? And that's according to NASA's exoplanet exploration. So the exoplanet, this is the Proxima Centauri b, which was discovered in 2016, has a mass that is about 1.27 times that of the Earth's. So it's not so different from the size of the Earth. There's so much to learn about, space exploration and exoplanets. But for now, we'll move on to our interview with Professor Robert Thompson. We'll be getting to know his background, his early life, his early school, undergraduate studies, and so on and so forth. So once again, it's really nice to have you in the studio here with us today. So would you please like to tell us about your early life, your background, where you born, and things like that?
Yeah, so it's a pleasure to be here today. Thanks again for the invite. So So I'm about as Scottish as they come, right? So my parents were Scottish, all my family are Scottish as far as I know. I was born in Edinburgh in 1978, and I lived there until I was 8. And then I moved to a very small village north of Glasgow called Blainfield. I'm not sure if you know it, Toommies.
No, I don't actually.
So nobody knows it unless they've grown up there, I think. But it's a lovely village in the countryside, and I went to the local high school, Balfron High School, and then after that I went to university. And the university I chose to go to was Heriot Watt.
Yay!
And I did an undergraduate degree in physics there. And then I decided that I wanted to learn more about a particular area of physics, photonics, that we both work in. And so I did a postgraduate degree that was run jointly between St Andrews and Heriot Watt. And after that I went into industry, and I had absolutely no intention of being an academic. There was no part of me that considered being a professor of physics or photonics at all. So I went into industry and had a fantastic job, was very happy, and then unfortunately the company that I worked for at the time, there was a sort of crash in the particular industry.
I see.
And so, many of us lost our jobs at that time, and I was very young at that point. I was 20, I guess I must have been 22, 23, and so I just looked upon this as an opportunity. And I said to my girlfriend, who's my wife now, I said, right, okay, let's go traveling for a year and work out what we really want to do. So we find, if my children ever listen to this, don't do this. But we got out lots of credit cards and loans, and went away traveling for a year, and then built up lots of debt, which is exactly what you're not supposed to do, and came back and then decided that actually I wanted to do a PhD, and that started me off on the research career.
I see. Wow, that's really interesting. I thought it was interesting as well that the fact that you spent some time working in industry as well. I'm sure that really built up your kind of background as well for the academic career that you are doing so well in at this time. Fantastic. And so in your PhD studies then, what drove you in terms of the scientific question that kind of spurred you on to pursue that?
Yeah, so that's an interesting question. So I had seen, both when I was doing my master's degree, particularly doing the industrial placement as part of my master's degree, the photonics aspect, so for listeners who are wondering what photonics is, one possible branch of photonics, I should say, I guess semi-definition of photonic technologies would be technologies that kind of do the optical equivalent of electronics. I mean, it's broader than that, but certainly photonic technologies would include those technologies that manipulate photons, right? Yes. Which are particles of light. They manipulate those photons in an analogous way to the manner in which integrated circuits manipulate electrons. Okay, so I did my master's project in a photonics company, and I really liked these photonic technologies, right? So I just thought they were super cool and really exciting, and so then I said, right, I want to do a PhD in photonics. And I looked around, as one does when they're looking for a PhD position, and the one that was in that area that I was most excited by was at Heriot Watt. So I came back to Heriot Watt in 2002 to start a PhD in effectively in integrated optics. And the particular type of integrated optics I was looking at was the development of devices called erbium doped waveguide amplifiers. Okay, so in telecommunications, we have lots of components that enable us to send information around using light. These include detectors and optical fibers and etc. Lots of different technologies, but one of the key technologies is amplifiers, right? Because the fibers that you send light with are not lossless, right? The light itself becomes attenuated as it propagates down the fiber. So you need a way to amplify the light so that it can then propagate further. So the erbium doped fiber amplifier is key to large haul telecommunications. Yes. But at the time of when I started my PhD, people were interested in making integrated versions of these fiber amplifiers. So my PhD was all about looking at kind of exciting ways that one could manufacture and develop erbium doped waveguide amplifiers, which are the integrated version of the fiber amplifiers used in long haul telecommunications.
Fantastic. That's lovely. That's great. So before we get even deeper into some of the technical aspects of your research, could you share with us what would you say is the biggest you're laughing already. What would you say is the biggest Eureka moment in your career so far? I know that's a bit of a random one, but what would you say? Is there any such thing that you say, wow, that was the moment that you were like, yes?
It's just an incredibly difficult question, isn't it, Toomese? I mean, we're both scientists, right? So, if I was to ask you, what are you most excited about in your career so far? I can tell you what you would say without knowing anything. I mean, I know a little bit about what you've worked on over the years, of course, but without, even if I didn't know those topics, I could tell you right now what the most exciting thing is, and what you would say almost certainly is the thing you're working on right now, right? That's at least that's what I would predict, right? So
yes. So, but what's yours then?
So for me right now, I'm just super excited by some of the work we're doing on using advanced laser manufacturing techniques to make devices called optical fiber preforms. Okay, so these are so when you make an optical fiber, what you have to do is you make something called a preform first, which is effectively a short, fat version of the fiber, right? And then you put it into a furnace and you heat it up, and then you pull the fiber from the end of it, okay?
And it keeps the structure, doesn't it?
And it keeps the structure,
exactly,
right?
So.
Exactly. The way in which these fiber preforms are manufactured is matched to the particular type of fiber that one wants to draw, okay? So conventional optical fibers are they have quite a simple structure. They have a circular geometry, and in the middle there's a core which guides light through total internal reflection, okay? The light bounces down the inside of the core because the core has a higher refractive index than the cladding, okay? And the routes to manufacture those types of optical fiber and the routes to manufacture the preforms from which those fibers are drawn is quite well established. What we're actually interested in is a new type, relatively new type of optical fiber, and these are microstructured optical fibers, okay? So in that case, what you can do is you can make an optical fiber where the entire fiber is made using one type of glass, okay? And what you do is you basically control the microstructure of the fiber, so it has, on the micron scale, it has some very fine structuring, that basically means that the light is trapped inside a hollow core. And that's a bit weird, right? Because, if you think about a normal optical fiber, it has this core with a high refractive index, and you can easily understand how the light, propagates
in the glass.
Yeah. Whereas with these microstructured optical fibers, the core is actually hollow. I mean, there's nothing there. And so what you basically do is you engineer the cladding surrounding the core with this microstructure that effectively means that, like, the light is surrounded by little mirrors. That's a good way to think about it.
So
now,
it's confined.
yeah, so the way that these fibers are, or more specifically, the way that the preforms are manufactured to make these optical fibers is using a technique called stack and draw, right? So what you do is you get ultra pure rods and capillaries of silica glass, and then you stack them, and then if you do that precisely, it creates the preform, and then you heat and pull the fiber from that preform. And that's a remarkable technique, but there are lots of reasons why one would wish to move to a manufacturing technology that, is let's say more precise or more repeatable and so on. And so actually one of the postdoctoral scholars in my research group, Callum Ross, he's developed a completely new way that we can use advanced laser manufacturing techniques to take wafers or glass substrates and directly write these preforms into the glass. I mean, it's just incredible. And I think that this has transformative capability. I really think that this could be an entirely new way to make completely repeatable preforms for this application.
Fantastic. Thank you very much for sharing that with us. Of course, we're going to get more into that later on in the show. You are listening to The Science Show with Dr. Dada on Jambo Radio Scotland. And we're in the middle of a discussion with our guest, Professor Robert Thompson from Heriot-Watt University. And now we're just going to take our discussion and focus on astrophotonics. So, Professor Robert Thompson, would you care to explain to us in very simple terms what astrophotonics is all about?
Yeah, so the field of astrophotonics, so if you remember what I was saying earlier on in our interview about, one area of photonics is the fact that we can actually implement optical function in a way that's kind of analogous to the way that integrated circuits manipulate electrons, right? So the idea of astrophotonics is really to harness the functionality that photonics provides to enhance optical instruments for astronomical applications. And there are good reasons why one may wish to do this. For example, stability of the instrument, or in some cases the cost or the functionality. Maybe there are things that photonics can do that simply are not possible to do using current technologies. But one of the most important reasons is actually the size of instruments, okay? And so what we are finding is that as telescopes get bigger and bigger and bigger and bigger, actually the instruments have to get bigger and bigger and bigger and bigger as well. And so there are hopes that actually photonic approaches with their integrated capabilities can actually enable much smaller instruments as well. And that comes with many, many benefits.
Yes, I'm sure that includes costs as well.
Yeah, exactly.
So
but also stability, and potential improvements in the information that you can get from the instrument as well.
Great. So I read in your group on your group page that some of the instruments you're developing are helping to study exoplanets. So the question is, what exoplanets have you been able to kind of help study with your devices? And do you have any insights, any new insights as a result of using these integrated sort of devices?
Yeah, so good question. So I would say that the field of astrophotonics in general is still rather new, but
I see.
what is certainly the case is that there are exciting capabilities that are coming to the fore now, and so what we've been able to do in my group, working with other groups around the world, is actually conceive, develop new astrophotonic instruments and then translate them onto telescopes around the world.
Okay.
And then demonstrate feasibility. And so by doing that, what we really hope to do is actually build confidence in these new approaches.
Yes.
And then once the scientific community gains confidence, then the hope will be that we'll be able to effectively win money to then build what we call facility class instruments. So these are instruments that would be permanently installed at a telescope and then would deliver world-class science over a long period of time.
I see. Wow, that's really great, fantastic. So the other thing I wanted to ask about was beam combining in your devices. So obviously, studying exoplanets, for example, involves collecting light, from space and analyzing the light in some way. So would you like to tell our audience how, just a basic idea of how this kind of works?
Wow, that's a really difficult question to me, because so interferometry. Okay, so where to start with this? So how would one detect an exoplanet? Okay, well, I guess the first option would be to simply look with a telescope and see if you can see it. Okay, and that can be done. Okay, so direct imaging of exoplanet systems can be done, and some of the most beautiful images that I've seen in science are of multi-planet systems orbiting stars. And it's stunning, but there are big challenges with that, because the planets are not bright compared to the star that's incredibly bright, and so you need to use instruments called coronagraphs that then block out the star, and there are limitations on how small the planet is that you can look at, etc., etc., etc. And in particular, there are limitations on how close the star can be to the planet because of this contrast issue. The other issue is that it doesn't provide information about the mass of the planet, right? Because really, I think it would be fair to say that most exoplanet scientists eventually, well, not eventually, I mean, they're interested in looking for Earth-like planets, right?
Yes.
I mean, and so really, to identify Earth-like planets, you have to look at not just the distance from the planet to the star, okay, because you're looking for planets in the so-called Goldilocks zone, where it's not too hot that there's that all the water's been vaporized, and it's not too cold that all the water's ice. So you're looking for planets in the right radius and orbit around the star. But those planets could be gaseous, or they could be rocky. And as far as we know, to have life, we need rocky planets. How do we know that? Well, okay, we only have one data point, and that data point is our own planet, and we know it's rocky, right? So we think we have to look for rocky planets of a particular mass in a particular orbit. And so to do that, you need to use a technique called radial velocity measurements, okay? And basically the way a radial velocity measurement works is that what you do is you look at the spectrum of the star, okay, as the planet is orbiting around the star, and even though you think the planet kind of sits in the middle and the planet orbits round, that's actually not what happens, right? Both the star and the planet are orbiting around a common center of mass, okay? So if you look at the star in the plane of the orbit, what you will find is that the planet is sort of moving towards and away from you periodically. And then if you measure its spectrum, you can then measure the amount of that orbit that the star is doing through something called the Doppler shift, right? And the Doppler shift is the same change in the pitch an ambulance you hear as it comes towards you and then goes away. Right, exactly. And that process exactly happens in the optical domain as well, okay? So you can measure that change in the spectrum of the starlight, and from that you can then infer what the mass of the planet is, because the more massive the planet is, the more it wobbles the star.
Yes.
Okay, so you can directly image using coronagraphs, and you can measure the mass of the planet using radial velocity measurements. But if you really want to do very high resolution imaging of things, eventually exoplanets, for example, then how do you do very high resolution imaging? And that's an interesting problem, right? Because to make higher and higher and higher resolution images, effectively what you need is a bigger and bigger and bigger telescope, right? So the angular resolution of an image is dependent on lambda over d. Lambda is the wavelength of the light,
or the color of the light.
Yeah, the color of the light, and d is the size of the telescope. Okay, now even the biggest telescope that's being planned just now, the extremely large telescope is what it's called, in Chile. It has a mirror of like 40 odd meters. Okay, so it's really, really big. Okay, but that's kind of approaching the types of limitations one could imagine for the size of a telescope.
Indeed.
If you want to go to even higher resolution images, so you need a bigger and bigger and bigger telescope, how can you possibly do that? And so the solution to do that is a technique called interferometry. Okay, and so what interferometry does is it basically says, right, okay, building big telescopes, great fun, amazing things can be done, but there's a limit. So what we're going to do instead is we're actually just going to build smaller telescopes, and we're going to space them really far apart. Okay, and then what we're going to do is we're going to basically look at how similar the light is between those two telescopes. So we're going to interfere it together. Now this technique of interferometry is already used in radio telescopes, right? Okay, and in that case you can place your telescopes, across the surface of the Earth.
Yes.
And because the frequency of the light, because remember, radio waves are still a kind of light, they're electromagnetic waves,
yeah.
but the frequency is much lower. So you can just record that effectively on a computer, and then you can process it later in a computer. Whereas in the optical domain, the frequency of the light is too high to do that, effectively too high to do that. So what you need to do is interfere the light from these telescopes together, and from that you can then reconstruct a very, very high resolution image of what you're looking at.
That's fantastic. So this interference process basically means superimposing beams on each other, isn't it?
Yeah.
And then the effect happens that kind of gives you the resolution. That's fantastic. So I understand then that you do that in your devices. You make devices that allow you to combine beams.
Yeah.
So how many of the beams do you have to combine in the devices?
Well, so to construct an image, you effectively need more than two telescopes, right? Because if you can think about two telescopes looking up and you interfere them together, basically all they're telling you about is telling you about how the sky intensity varies along one axis, okay, or along one baseline, where the baseline is defined as connecting the two telescopes, right? To reconstruct a two-dimensional image, you need more than two telescopes, okay? So the more telescopes you combine, the more complete your image actually can become. Now there are some little tricks that we can play there as well, because remember, as the planet, as Earth is rotating during the night, then effectively you're kind of sampling the sky with many more baselines. Okay, so this has a complex name that, and for reasons I won't go into, but basically what it does is it allows you to effectively fill up the information that you can gather as if you had many more than just your 3 or 4 telescopes. So for example, at the VLTI in Chile, the Very Large Telescope Interferometer, they have multiple telescopes, I think up to 6 telescopes that they can combine coherently into a photonic chip to do the interferometry.
Wow, that's fantastic. That's really, really exciting stuff. Thanks for sharing it with us, Robert. And the other thing I wanted to ask about is the fact that, obviously your devices are not just applicable to astrophotonics, as you've mentioned, but there's an aspect that's maybe very interesting for everyone else, which is also to do with clinical photonics. So would you like to say one or two things about that very briefly?
Yeah, so the group that I lead, the photonic instrumentation group, right? So really, we're not fundamental scientists, okay? So in the sense that we are pulled by applications. We're applied physicists, we're engineers, we're interested in solving problems, right? So those problems exist, for example, in astronomy, in astronomical instruments. We're trying to solve those problems with photonic technologies. I talked about the fiber preform work, where we're trying to solve a problem with manufacturing these fibers. But another application area that we're very interested in is clinical photonics. So developing and harnessing the power of fiber optics or other types of photonic technology to then enable, for example, diagnostics or tools for experimental medicine that really open up capabilities that otherwise are impossible. So I think a good example, if you'd like me to give you an example.
Yes, that would be great.
Yeah, so a good example there would be some work that we've done over the last few years on developing fiber optic devices. So a photonic device, a fiber optic, that we can then, at the end of the fiber, we can place tiny little sensors, that are micron scaled, in some cases even nanoscaled, that have properties that mean that their fluorescent emission changes depending on the pH of the local environment. So the pH is a measure of the acidity or the alkalinity of the local environment. So what we do is we send light down the optical fiber, okay, at the distal end, so the end that's in the lung, for example. We can then excite these little sensors. They then fluoresce light or emit light in some other way, and then that light comes back up the optical fiber and tells us what the microenvironment is at the end of the fiber. Now, why would we want to do that? Well, actually, it's very timely, because obviously we've just gone through the situation with COVID, and and so there's a lot of interest now about really having tools that allow us to probe the microenvironment, particularly down in the very bottom of the lung, called the alveolar space. So these are the gas exchanging regions of the lung, because what happens in some diseases is that actually your own immune system can go a bit wonky, okay? And when it does that, you have cells that come into the alveolar space, and they then secrete things that change the microenvironment, okay? And with these fiber optic sensors, we aim to actually sense those changes, and that should provide information to clinician scientists, more precise information about, for example, what the immune system is doing in those critically important regions of the lung.
Yes, fantastic. It's great to see so many areas, that you can touch with just the research that you're doing in the PHI group at Heriot-Watt University. So, in the long term, then, what could things look like for your research? Like, where would you like to see? What's the future for the instrumentation that you develop, for example?
So as I said, we're not fundamental scientists. We're applied physicists, and we're really engineers in many ways. And so if you're pulled by an application and you're pulled by a problem, then clearly you want to solve that problem. And if you want to solve the problem, you want to see the problem solved, and you want to see the end product. So, I think on the astro side of what we do in the group, the end goal has to be significant astrophysical results coming out. Yeah. So we need to take the concepts and devices and the technologies and the proof of concept instruments, but that's not enough. They need to go forward into actual instruments that then deliver astrophysical results. Yeah. And similarly for everything else that we do as well, developing a technique for making optical fiber preforms, well, that's great, and getting a paper out of that is great, but actually, it doesn't really mean that much unless you do something real with it, I feel. Yes. And similarly for the clinical photonics work as well, it either has to provide improved healthcare for patients, or it has to improve understanding for clinician scientists of the disease, to then result in improved care for patients. So from my perspective, it always has to eventually result in some real world impact.
Real world impact. In fact, that's great. Thank you very much, Professor Thompson, for that. So we've come to near the conclusion of our show for today. But before we go, we're going to enjoy a couple of science jokes. So we'll ask you first, do you have any science jokes that you find as your favorites, or anyone that you can share? It's okay if you don't, but do you have any?
I do have one.
Yes, go on.
I'm going to get it wrong now.
No, don't worry. Yeah. Go for it.
So an atom walks into a bar.
Yes.
And the barman says, "Oh, you're looking so down. Why are you looking so down?" and the atom says, "Oh, I've lost an electron." And the barman goes, "Oh no, are you sure?" And the atom says, "Yes, I'm positive."
Great. Yeah, that's a good one, isn't it? I think most people understand that one. What do you think? So when the atom loses an electron, it becomes positive. And then it's positive in the sense that it's sure that it's lost an electron. So it's kind of a play on words there, isn't it? Fantastic. So going back to the question for the week that we asked. So what is a light year? What on earth is a light year? There's a not so serious answer to that question. And that answer is, the devil is in the details, because the question was, what on earth is a light year? So what's the answer? What do you think? Can you guess? Oh, it's a bit of a joke.
What on earth is a light year?
It's a bit of a trick question, that one.
Oh, I don't know. I mean, I was when you were talking about distances and so on, I was trying to think about, so I know that light travels 3 times the circumference of the Earth in a second, right? So in a minute.
Okay, I'll say the answer. You're getting too technical. Yes. So the answer is this. Well, it is the same as a regular year, but with lower calories. So that's a light year for you. So the lighter side of the question. Great. So I think that's all that time will allow us to do. So yes, the next thing we're going to do to conclude the show is to sing a song. And Professor, if you'd like to, I'm just kidding. I'll attempt to do a freestyle on a beat. Something about what we've talked about, right? Okay. Let's see how this goes. So please, DJ, if you could give us the beat. Actually, could we have another beat? The relaxed beat. Yeah, so I want to do a bit of Afrobeats on this one. Yeah, this one. Yeah. All right. So today we talk about ultra fast inscription, right? And what's the wavelength of the lasers you use?
1 micron.
1 micron. So that's a bit in the infrared, isn't it?
Yeah.
Yeah. Okay. Let's see what we can do. So something like yeah. Yeah. Ultra fast inscription. Yeah. Using 1 micron laser. Yeah. K-band beam combiners. Yeah. From Astrophotonics, you look at exoplanets to fundamental optics. Yeah. Now, can you repeat after me? Yeah. Well, that's all that time will allow us to do today on the Science Show on Jambo Radio with Dr. Dada. Next week, we hope to have another special guest on the show, and we'll continue on the theme of astrophysics. We'll be talking about something that's beyond the stars and about the dawn of time. So we look forward to that. So please tune in to us the same time next week for another exciting edition of the Science Show with Dr. Dada. Until then, stay curious.